So, a very good morning to all. I'm Rahul from the Indian Statistical Institute in Kolkata, and my work focuses on the persistent tensions in cosmological observations. So, to begin with, this is a brief introduction to our whole existence, our universe, and it is an overused graphic which shows the evolutionary history of a universe. And we are somewhere on the right hand side here looking back in time. And we can measure the expansion of the universe at different eras using different observations. But today, I'm concerned with the measurement of the Hubble constant, which is the rate of expansion of the universe today. This was first measured by Edwin Hubble in 1929 to be about 500 units using observations of nearby galaxies. But today we have come a long way and we have made significant progress both technologically and scientifically. And these are some of the different methods to measure the Hubble constant today. And if you see on the right, the measurements are very precise. This precision is, however, a curse in disguise because there seems to be a disagreement between early time lambda CDM based measurements versus direct late time measurements. And this is a problem that has only gotten worse over the last decade, and there have been multiple theoretical propositions to help solve the problem. At the same time, there are people who blame experimentalists. There have been studies on claiming that there have been studies on overlooked systematic biases in experiments, but neither approach has been able to give a satisfactory solution to the problem yet. So this problem is not between just one experiment and the other. It is between two groups of experiments, early time versus late time. And the claimed solutions till now are often overstated or, dare I say, just plain wrong. Now, as I mentioned, there are several models that have claimed to have addressed the Hubble tension to some extent or the other. We took these 6 representative models for further studies, just to demonstrate our working principle. And we tried to see what is their status against latest available datasets. Now, we do this exercise because of 2 reasons. One, the existing constraints in the literature are either with outdated datasets, or maybe in some analysis, they have not used all the major datasets that need to be used. So we bring all of them on the same footing by using the 3 major datasets, the CMB from Planck, Galaxy Bow data, and the Pantheon supernovae compilation. I'll come back to these constraints very soon. Right. So the tension is between early and late. What happens at the Middle Ages? I mean, in terms of redshift, Middle Ages would translate to about 5 or 6 or 7 when the universe was half its age it is today. And we refer to these as intermediate redshifts. And on the right, these are just some of the physical phenomena which could help us probe such distances directly and maybe infer the Hubble constant. And there are a plethora of missions, upcoming missions, with some of them already launched, which can help us get data from intermediate redshifts. But today, I'll only focus on gravitational waves. And why are these interesting? These are interesting because gravitational waves can travel much further unimpeded compared to electromagnetic signals. Also, GWs will help measure the Hubble constant both at low redshift and at intermediate redshift. Now, the low redshift measurement is expected to not be very different from the other direct measurements of around 73 or so. But what is more important is the value we would get from GWs originating at intermediate redshifts. This can perhaps settle the debate in either's favor, 67 or 73, or maybe the value would be bang in the middle, and that would be interesting in and of itself. So it is, in any case, it would be lucrative to measure H0 with GWs at such redshifts. So before proceeding, just a small note as to how H0 is obtained with GWs. So gravitational waves are called standard candles. So given the detected waveform of a signal, it is possible to directly infer the luminosity distance of the source of the wave. All that remains is to find the redshift by some means or the other, either through an electromagnetic counterpart or by galaxy correlation, statistical correlation or something. If you have that, if you have the distance and the redshift, you can find the Hubble constant. Of course, the simple Hubble's law does not work here, since we are not talking about very low redshifts. So we have to use what I call the modified Hubble's law. This is a very familiar expression to the audience here, where omega naught matter is the present day matter density, and the second term signifies the evolution of dark energy density, which is itself parameterized by the equation of state of dark energy. Right. Now, Observing these gravitational waves from intermediate ratios is not possible today yet. We don't have the technology, but it will be possible in the future. But what we can do now is to simulate some mock universes, or rather to simulate some mock data sets, and then do a forecast study on them. And that is the goal in this work that we had. So to generate the mock data sets, you need three ingredients. You need to have an idea of the distribution of the source population. You need to know the, if I may say, the least count of the instrument that you're considering, and you need to assume an underlying fiducial cosmological model, along with the current constraints from current data sets as priors. So we use the 6 different models, as I showed earlier, and do our forecasting using a three-pronged approach, which is the crux of this work, by generating mock catalogs in the context of the future GW mission, LISA. So we do the forecasting in 3 methods. The first one is the traditional Fisher forecast, which gives us the optimistic estimate on the errors on the Hubble constant based on the instrumental specifications. In the second approach, what we could do is we could pretend that the mock data is real data and do the usual parameter estimation using MCMC. In this case, we get constraints on both the mean and the error on the Hubble constant. However, the results are dependent on the cosmological model we assume to obtain the set constraints. So we wanted to see if there is a way to get rid of this explicit model dependence. So we attempted to do a non-parametric reconstruction of the Hubble parameter itself. And we did this using the machine learning tool Gaussian processes. It cannot constrain the other cosmological parameters as usual, but the y-intercept of the reconstruction gives us the Hubble constant in a completely non-parametric way. And here are the results. Pretty boring slide, but please bear with me. So these are the tension values that I quote for each case. The first row are the tensions with current data sets. Fisher, however, you will notice for each of the models, each of the fiducials shows an increased tension. But this is not a bad thing. This is good. This only indicates that LISA would be more constraining on the Hubble constant than all current data sets combined. So that is itself one of the reasons we should be looking forward to this mission in measuring the Hubble constant. Coming to MCMC, the tensions are more or less similar with current data sets, and that is good because it helps act as a consistency check that we are not doing anything funny during our mock generation process. The tensions have reduced a little bit due to minor, widening of errors and very insignificant mean shift. But the most interesting thing happens for Gaussian processes. You see the errors have gone down a lot. The tensions have gone down a lot. This is one of the reasons for that is the error bars have inflated. Fine. But the other thing that we noticed is for each of the cases, there is a shift in H0 mean value towards the higher value, towards the Schuh's value. But this is very, very surprising because in the entire analysis, we have not used any late time prior. So what does this mean? Doing a non-parametric analysis, why does it show this upward trend? To be very honest, we do not know. We haven't been able to understand why this is happening, and we leave it as an open question for future work. And this is just the same thing, a bit more visually for 3 different mission durations of LISA. As you can see, the results are qualitatively same, only the error bars shrink the longer the mission runs, which is expected. Right. So the main takeaway from this work, this first project that I am presenting is we urge the community to carry out forecasts using different methods so as to comparatively weigh and outweigh the pros and cons of each, and hence get a fuller picture of the physics at work and not just be limited to Fisher. Right. So moving on to the second part of my talk is at the end of this work, we had some questions. And the questions were, why is the shift happening? This is one. And also we thought whether these results are dependent on the fiducials that we are using. And also whether these results are dependent on the mission that we are considering. So what we did was to study the role of 2 completely different GW missions with completely different systematics. The Einstein telescope, which is a the ground-based mission, and the LISA, which is a space-based mission. And also we considered 2 distinct set of fiducial values obtained from early time datasets and late time datasets separately. And here are the results for this. It's a heavy slide, but please again bear with me. So I would bring your attention to the top left plot, you will see that ET can constrain the Hubble parameter quite well till about redshift of 1.5 or 2. This is because it has a very high number density in the sense of detected events. It will detect around 1,000. It is expected to detect around 1,000 events in 2 years time. And but LISA,
you have 2 minutes.
Thank you. But LISA, on the other hand, will have a lower data density, but it will be able to see much further and help in our goal of looking into intermediate redshifts. And if you go on the right, this shows the evolution in the constraining power of each of these missions on H0 as the mission duration increases or as more and more number of events are detected. So this is obvious. The more number of events you have, the tighter the errors would be. But what is interesting is in some of the cases, you will see that even for the different fiducials, after a certain number of events, they kind of overlap. Now, does this mean it will solve the tension? Well, it's a forecast analysis, so such a strong statement should not be made, but it is something that we are saying is very exciting to wait and look forward to once the real data comes in. So just to quickly wrap up this part, is we can comment that GPs are robust as a non-parametric tool and is sensitive to the fiducial inputs in the mock data. Moreover, we see that both LISA and ET would be more constraining on the Hubble constant than all current datasets, and a 10-year LISA run would be comparable in precision to a 3-year ET run. And finally, the longer the missions run, the better the reconstruction and hence the better the constraints. So let me end with this slide by saying that the Hubble tension is a notorious problem, and it's a problem that keeps on giving, with there being innumerable papers being written about it. Since there has been no satisfactory explanation yet, we think maybe intermediate probes are the way to go. Let's see, we just have to wait and see. Also, I feel machine learning will play a pivotal role in understanding these problems, but much work is still left to be done. And finally, tensions are bad. They make us look bad because it means we as cosmologists are probably not doing our jobs very well. But at the same time, these are opportunities for novelty and discovery, and that is what makes them exciting. If you have any questions, I'll try my best to answer them. And more importantly, if you have any comments, please feel free to let me know now on Slack or write to me later. Thank you.
Thank you, Rahul. Any questions or comments? Anyone in online? Okay. So if no, I want to ask, so you make this analysis in 3 independent way, right? So yes. This MCMC, ML, and the frequency analysis is done separately.
Yes, absolutely.
And you do it only for one to estimate one particular parameter, H0.
We are focusing on H0, yes.
Okay, understood. So is it possible to combine all the 3 and get the maximum out of it?
Okay. Combine in the sense each of them are giving me estimates on H0 independently, but in what sense would you mean combine? Because I have, let's say, a mock data set. For that, if I do Fisher matrix forecasting, I only get an estimate on the errors on H0. If I do an MCMC, I get a model dependent estimate on H0 with the mean and the error. And if I do this, then I get the full reconstruction of H of Z, the y-intercept of which will give me H0. So I don't suppose a combination would tell us much, but rather I want to say that using Fisher, we get to know that LISA would be very constraining. Using MCMC, it helps as a consistency check in our mock generation, whether we are doing the mock generation correctly, and GPs help us do it in a non-parametric manner. I guess that is the winning point of each of these methods.
Okay. So any more questions? Okay. If no, let's thank Rahul again.
Thank you.